the inner planetary system, in the inner solar system. Because in fact it moves a lot, but after it can reach area in the solar system when you are when you can have some
perturbation.
But it's a very important effect, and we know that it's very fundamental to make evolve this kind of orbits.
Say it. What is the word in French? Chaotic?
No. I even don't remember.
Sorry. Okay.
It's
Later, when you think of it, it'll come later.
Yeah. Okay, so let's try to finish anyway. Thank you. It's a resonance between mainly Jupiter. So in fact, it can drift the orbit to resonance, so mainly resonance 2 to 1 or 3 to 1 with Jupiter. So when there's a resonance, we have a big change in orbits. Some question?
Question, yes.
Yes.
To be sure I understand, you chose 1998 KU2 because it's an F-type asteroid? Is that why?
No, we know it before because we just chose it because it has a good orbit, and after they make a spectrum, and it was the same. So it just.
Oh, you mean so you said what orbit of the asteroids could possibly evolve into this?
And after we observed it, and we saw it is the same.
Oh,
so that's good.
Yeah, that's very. Yeah, I didn't realize that. Thank you.
Thank you. And the next speaker is Mark.
Okay. My great thanks, my appreciation for the Faculty of Sciences and for the students here for their extraordinary friendship and hospitality. This has really been a wonderful trip. And I know everybody else feels the same way. This is extraordinary. And also I'd like to congratulate you on really a truly amazing achievement in recovering the Alma-Hadasset meteorites. This is, of course, as you can see, unprecedented. And congratulations to you. It's my pleasure to be here, of course, as I think I've just expressed. Before I begin my talk, I think I'll give a little introduction into my own interests in meteorites. I've worked on asteroids for almost 20 years now, and meteorites are intimately connected with asteroids. But it was a little while after I began work at the Adler Planetarium in Chicago, where I've been for over 7 years now, that an extraordinary event happened in the Chicago area. And here are some videos that illustrate this event. On March 26, 2003, just before midnight. This might look a little familiar to you. The sky lighting up like daytime. Midnight sky like daytime. From downstate Illinois, looking up towards Chicago. From Michigan, 160 kilometers away. Again, lighting up the sky like daytime. This was the impact of the Part5 meteorite. Now, the next morning, I got any number of calls, many calls, from people in that area who said their house had been hit by a meteorite or their car had been hit by a meteorite. And oftentimes I would get people calling me up, oh, I found a meteorite. And never, ever was it the case. It was always some other rock. But here, several people calling up, and extraordinary stories. So I thought I would go check it out. So I went down to Part5, where one man who said that his house had been hit, I came up there and I saw these repair people working on the roof. I knew something was up. And he showed me inside. He showed me there was a hole in the ceiling. A hole in the roof, hole in the ceiling. It had bounced off of the kitchen wall and made a hole in the kitchen floor. Went all the way down into the basement. punched a hole in the basement, in the ceiling there, in the floor, cracked this rafter, bent the pipe, bounced off the floor, and landed in a pile of laundry. This was the second largest fragment recovered from the Part5 meteorite fall. And I'm very happy to say that we have this meteorite on display at the Adler Planetarium in Chicago, where it's viewed by 400,000 people a year. This is a very important, for us, this is a very important piece of local astronomical history. And so I'm very happy that we can share this with the public. But this is the thing that really galvanized my interest in meteorites as a connection to asteroids. And just a separate note here, talking about strewn fields. This is the strewn field of the Part5 meteorite. You can see it's very discontinuous, that there are breaks in the distribution. And what's important to note, though, is where the meteorites were found and where they weren't found. They were found where there were houses and streets. This area here in the middle of the strewn field is a small forest preserve. No fragments were recorded in there. This field was probably continuous. There are fragments here in the grass, fragments here in the forest, and they remain there today. Hundreds, if not thousands, of fragments of meteorites. Less than an hour from Chicago.
Should we
Recovering
go?
meteorites
Should we go
is a tough, yeah, let's all go to Chicago. This is a tough job. Believe me, I understand it. Oh, and another point of interest too. The University of Chicago meteoriticist Steve Simon, whose paper this is from, he lives in Part5. His house is in the middle of the strewn field. He didn't have any meteorites in his house or in his yard at all. That's terrible irony, isn't it? But onto my main talk here. I'm going to talk about the prospects. What are our hopes for identifying the parent bodies of Uri-like meteorites? And I'll begin by giving a history of this connection that people have often tried to make between meteorites, specific meteorite types, and a specific asteroid. This is a very favorite pastime, a hobby of planetary scientists, sometimes I think too much so. The prime example goes back to 1970 with the connection between the spectrum of Vesta and the HED meteorites, the basaltic chondrites. And this connection was facilitated by the distinctive chemistry of the silicate minerals. This is a very strong signature of pyroxene here. We have the distinctive 1 micron and 2 micron features. Now the benefit of getting beautiful spectra like the spectrophotometry here, spectra of the meteorites, is that details in the spectra, like the location and depth of these absorption bands, can give you specific details on silicate chemistry. And I think that that kind of thing is very important for forging a definitive connection. Now Vesta is not alone though. Vesta's orbit is shared by dozens of known, if not hundreds or if thousands that haven't been confirmed yet, of objects that appear to be chips off of Vesta. These are asteroids that are dynamically associated in many cases, and in some cases they're not dynamically associated. So, but many of them appear to be connected with Vesta. They have very similar spectra, some differences that we still have a hard time understanding. When we look at the distribution and orbits of these pieces, we see that indeed most are associated with Vesta here, but there are a few that are located a ways off in orbital element space. These may be dynamically isolated. The ones that especially are interesting are the ones that are located on the opposite side of the major motion resonances. Yes?
I know what is inactive, but
Oh yeah, indeed. Okay, so what this is a plot of the proper orbital elements. So the long-term average orbital elements of the asteroids. And this axis here is this is the semi-major axis, the size of the orbit of the asteroids. This is the eccentricity. No, I'm sorry, this is the inclination, how tilted the orbit is. When you do a plot like this, you can see clumping in the distribution of asteroids. These are the collisional families. These are the remnants of catastrophic collisions between asteroids. And the Vesta family is one such. And it should be no particular surprise that most of those asteroids in this region appear to share a similar spectrum. Now, these mean motion resonances, these are very fast delivery routes for asteroids into near-Earth space, meteorites into Earth collision. But it's also difficult for asteroids to cross them by long-term diffusive processes like the Yarkovsky effect. And so when you find asteroids that are located across the strong 3-to-1 mean motion resonance, it makes you wonder, how could this asteroid have evolved away from Vesta? Could this one here out in the outer mean belt, asteroid Magna? It seems quite unlikely that these are chips off of Vesta. These objects are small, order of 10 kilometers, far too small for them to have differentiated, that is, been substantially or completely molten and had a basaltic crust. Far too small for that. These must represent fragments of a distinct, a separate parent body of basaltic material. And I'll throw a cautionary note here into this connection. And it's a little speculative, and frankly, I don't believe it. I'm just throwing it in as a cautionary note. That we start with this understanding. We know that most of the meteorites in our collection are relatively recent visitors to the planet Earth within the past few thousand, tens of thousands, hundreds of thousands of years. In terms of the grand scale, the age of our solar system, that's a very short time. That the delivery of meteoroids, small asteroids, into Earth orbit is dependent on things like the location of that asteroid relative to one of these delivery routes. And also dependent on the composition of the asteroid, which affects the strength of the Yarkovsky effect. Now, those together tell us that there's no reason to expect that the distribution of meteorite types that we see in our collections must necessarily represent the distribution of asteroid types that we see out there in the main belt or even the near-Earth object population. And given that, I'll ask this question. Could it be perhaps that most of the basaltic achondrites, the HEV meteorites, maybe they don't derive from Vesta, which is just the most obvious source. Maybe they come from one of these independent bodies, which just happens to be better located for delivering fragments to Earth. We don't know that for sure. This is the classic example of a connection between a specific meteorite type and a specific asteroid, and frankly, we don't know for sure if that's the way it is. There have been many more general connections. A classic one is this association between the carbonaceous chondrites and the C-type asteroids, based on a similarity in spectra. I don't even have the spectra shown here, because the spectra of these objects is relatively neutral, with no distinctive spectral absorption features throughout the visible to near infrared. They just have flat spectra with low albedos. That's not a lot to hang a connection on. M-type asteroids, there's another cautionary note here too. They have red-sloped spectra, moderate albedos. They have spectra that appear similar to nickel-iron metal, and therefore iron meteorites. This is a wonderful connection to be made. However, when you look in the infrared, you see that some of these M-type asteroids show evidence of having hydrated minerals on the surface, aqueous alteration. This is inconsistent with their origin in the core of the differentiated body. So are they really the parent bodies of iron meteorites? That seems quite unlikely. We don't understand this very well. Now on to Urielites. If we want to make a connection, we have to ask the question, make a connection between meteorites and asteroids, we have to ask, do the spectra contain recognizable and distinct features that will allow us to make this identification? We look at Urielite meteorites and we see that here's a handful in the collection. Here's Almahadasita. We see the spectra shows this pyroxene or olivine feature at about 1 micron, a hint of pyroxene at 2 microns. So we do see some distinctive features. We also see in the case of Almahazasita a relatively neutral spectrum in the visible. And the neutral spectrum in the visible, that's consistent with amorphous carbon or graphite, a low albedo material that's consistent with the brightness of this material. So we do see spectral features, and that will be important.
So why do you think the others are so steep?
Well, part of it I think is because their compositions are less carbon rich. No? Terrestrial weathering? Yeah, that's one reason.
That's the
And looking at the comparison of the spectrum of 2008 TC3 and Almahazasita, we see really a beautiful agreement. The spectrum here is spectrum provided by Peter. And the dots are the raw data from the asteroid spectrum. The green line is a median, smooth version, just to show a little bit better view of that. The red line is the meteorite. And really, once you scale them appropriately, just multiplying by a ratio, you get really a wonderful agreement. And I'll note that you get a beautiful agreement in the strength of this 1 micron absorption feature. There's even a hint that of a minor absorption feature being replicated in the asteroid spectrum, but I wouldn't stake my career on that. I then asked the question, have we seen any similar bodies in existing databases of spectra of asteroids? This work is in progress. I should note that my main collaborator on this project is a high school student who is interning with me. This is her year-long project. And so she's making really wonderful progress, but she still has 4 more months to go in this work. So this is definitely a work in progress. She's looked through 2 catalogs by Rick Benzel and his students at MIT for the Small Main Belt Asteroid Spectroscopic Survey. And we've looked there and have found no obvious candidates that match the spectra of the 2008 TC3 or Almahazasita. Now, part of that problem, though, in making that connection is that the spectral range is relatively limited, does not extend all the way out to 1 micron, and the spectra of the asteroids can be somewhat noisy. So we can't make a definitive statement on that. Now, we'll also look at spectrophotometric databases. I've done some work with the Sloan Digital Sky Survey in using the Moving Object Catalog. These are asteroids that were detected during the course of the survey. The survey, of course, was designed to look at distant galaxies and quasars, but in order to look at such distant objects, you have to look at everything in between you and the distant universe. And so this survey observed more than 400,000 asteroids in 5 different broadband filters throughout the visible up into the near infrared, almost 1 micron. And you can see these filters, the U, G, R, I, and Z here, and where they fall relative to a handful of representative spectra. And especially note that the Z filter falls in the region of this pyroxene or olivine absorption feature near 1 micron. So do we see any objects, any objects in this database that appear to be similar to Almahazasita or the Urielites? Well, just a quick look. Looking at asteroids that were observed by the Small Main Belt Asteroid Spectroscopic Survey. These are ones that have taxonomy associated with them. Synthesizing colors in the Sloan system and overlaying them on the Sloan detections, we see that, yes, indeed, we can distinguish certain taxonomic groups. And doing a similar thing, synthesizing photometry for meteorites, we see that the basaltic achondrites, which are a special interest to me from another project, do indeed show up in the Sloan data set And so you can use Sloan data to pick out candidates for follow-up work. Can we do a similar thing for uriolites? This is an example again of the work on the basaltic chondrites. The green targets, the green dots, are those that have a strong silicate absorption feature, like a P-type or basaltic object. Most appear to be associated with Vesta. There are a handful of objects in the middle and outer belt. We've been following those up. The red ones are ones that appear to be olivine rich, and those were some side interests. We spent most of our work working on the V-type objects, and so we really haven't looked at the A-type ones, which is kind of unfortunate given what I'll say here in a few slides. But the red ones, the A-type objects, don't appear to be concentrated in any region of the main belt. Where do urolites fall on these plots, comparing the filtered locations to the spectra of the meteorites? We see, yes, so the Z filter could pick out this absorption feature, and there is an excess in the U filter compared to, well, some of these other urolites. Synthesizing photometry for these and plotting these out on a color plot, the G filter minus the R filter, so that gives an idea of the spectral slope in the visible. The I minus Z, this gives an indication of the strength of the 1 micron absorption feature, with a stronger feature going down here. So you have the V-type asteroids here, S-type asteroids in this cloud, C-type asteroids in this cloud. Most of the urolites in the Relab catalog plot on the right-hand side of this plot. This is where we would find the A-type objects, the olivine-rich objects. That may not be very surprising, given the olivine-rich character of urolites. Alma-Hattasita, its spectrum is distinct, falls more towards the C-type, which may be not surprising because it has a relatively neutral spectral slope. But note that all of these have a near-infrared absorption feature that is moderate in strength. They're not completely neutral in the near-infrared. Looking in the U minus G, looking at the UV strength, we see that Alma-Hattasita falls has an excess in the UV, that the C-type cloud of objects extends a little in that direction. The F-types would be in this region. Alma-Hattasita is similar in this broadband photometry to the F-types. But looking at the plots though, and it's probably more a function of the errors in the database, just photometric errors, that I cannot identify any distinct population of objects in this data set that correspond to the urolites. The Alma-Hattasita-like objects, they be found near the F-type side of this C cloud. Part of the reason we can't identify the population is because these are relatively low albedo objects, and it may be that these small dark asteroids are just too faint for us to observe in the Sloan data set. And that I think we really need to have higher quality and simultaneous multicolor photometry. Now, our F-type asteroids, appearance of Alma-Hattasita-like urolites. Well, my conclusion really on that is that some of the urolite appearance may be in the catalogs as F asteroids. But when you look at the spectra, where spectra, not just photometry, are available, the spectra of F-type asteroids, and here are representative 2 of them from the SMAS2 catalog, none of the asteroids I've looked at show this 1 micron absorption feature that we see in the spectrum of 2008 TC3 and Alma-Hattasita. So calling it an F-type, I think, maybe maybe not good enough. I think maybe we need a new taxonomic class, if that makes any sense. Something that takes into account the information that we get from higher resolution spectra, and not just broadband photometry. I think instead of just looking for an excess in the UV, that we need to find something with an excess in the UV plus that absorption feature due to silicate-rich material. And the other Eurolites, in this initial analysis, they kind of look like A-type objects. Once again, a conclusion, no obvious candidates have been found in the existing spectroscopic catalogs. So no obvious distinct population also seen in the moving object catalog. For us to confidently identify parent bodies of Eurolites, will probably require higher quality spectra, higher resolution spectra than the existing broadband data that we have. And follow-up of the A or F-type targets, because there are so many objects out there that are definitely not Eurolites, may not be the most efficient way of finding the parent bodies of the Eurolites. And I think that is it. Thank you.
And I think of it in this way, and I like the story, so I'm going to share it if I can.
Please.
So think if you went to the grocery store and if you classified all the fruits and vegetables based on their color alone, which is what the asteroid taxonomy is, it's color. So then you'd say that bananas are like squash, or carrots are like oranges. And they have no relationship in terms of botany or anything else, except, so it's a false taxonomy. Well, the interpretation.
But apples are not oranges.
That's right, they're different. But the taxonomy is just the beginning. And when you interpret, you have to have physical quantities upon which you can make the interpretation. So the taxonomy is just the beginning.
I think that's a very good point, and building off of Peter's little comment there, that apples are not oranges, just because they happen to look alike, and with some basic information like color, doesn't necessarily mean that they're genetically related. But if they look different, there's a good possibility that they're different.
Ranimal Department of Zoology. Is the structural density of the TC3 support the hypothesis that all the at the beginning of the solar system, planets early rocks formed according to the density, so that it's structure according to the density, so that we say Mercury is a rocky, but Pluto is a gaseous. Is a Manhattan structure support this hypothesis? And is there was a planet, another hypothesis, a planet has been destroyed at that region? So that is the structure of the Manhattan to support this hypothesis? Thank you.
Well, I'm not sure I completely follow. Alma Hadasita is a differentiated meteorite. It comes from a differentiated body, something that was substantially molten, at least partially molten. And so it's an evolved body. The parent body of Alma Hadasita would not retain a pristine record of its formation circumstances. So it wouldn't be the best example to use to say what were the formation conditions in different regions of our solar system. For that, you would go to the carbonaceous chondrites, the primitive meteorites, ordinary chondrites even, and look at the distribution of their compositions throughout the solar system.